All right, so the solubility, oops, this is where we want to be. When we have any dissolving process occurring, we've talked about this before, but we have to remember that there is an equilibrium that occurs, an equilibrium. So in a solution that's, we say, is saturated, because you can see that there's some solid on the bottom here that's not dissolved, this solvent here is dissolving as much of this solution as you can. So this is a saturated solution. There is an equilibrium that occurs. So on the surface of these solid particles, some of them are going to be very crystalline in nature. Some of them are just going to be amorphous, not very perfect in terms of the degree of crystal-like character. Crystallinity, there it is. Either way, compounds are going to come off into solution, and other ones that are into solution, when they collide with the crystals or the solids, are going to try to become solid, because they have some intermolecular forces there. So this is always in an equilibrium. Solubility varies with temperature, and I think you probably have some experience with this in the kitchen. If you've ever made syrup before, you know that the recipe is like 2 cups of sugar for every 1 cup of water. And if you do that, it won't dissolve. You have to heat up the solution, and then heating up the water to pretty close to boiling will be enough to allow those 2 cups of sugar to dissolve in that 1 cup of water. And the result is what we call a super saturated solution, because even when you cool it down to room temperature, the resulting mixture, which is very thick, it's like a syrup, right, stays solubilized, okay? But again, an experience that will remind you that solutes dissolve into solvents differently based on temperature. Now, seeing the curves for all of these different materials here, you see that most, not all, but most solids increase their solubility with temperature. And that's our experience with table sugar as well, sucrose. But it's different with gas. So here's an example. During the Industrial Revolution, factories were built on rivers so that the rivers could use the water to cool the machinery. And the hot water was dumped back into the river. And after some time, the rivers began to be darkened and many fish died. And so people said, well, the factories are polluting the water, and they tried to look for different pollutants, but they couldn't find any. But it wasn't the pollution. Do you have any idea what it was, Fred?
What do you mean it wasn't the pollution?
Well, they weren't polluting it with chemicals that were harmful to fish or plant life in the water, right? What they were doing is they were releasing the hot water into the river, and that hot water was changing the solubility of oxygen. So for gases, if you heat the solution, gases decrease their solubility in water. So like in table or sugar, you heat the water, it increases the solubility of the sugar. If you're talking about gases, you heat the water and it decreases the solubility of a gas, like carbon dioxide. Have you ever had a soda pop that you left out all day?
Yeah.
Now, if it's sealed, then the carbon dioxide is still there and it still might be soluble a little bit. But if it's unsealed, then, and you heat it up, that carbon dioxide will come out of the solution very quickly. So carbon dioxide's solubility in water is dependent on its temperature. And the higher the temperature, the lower the solubility of carbon dioxide, that gas, in water, in the solvent. All right. Now, talking about carbon dioxide dissolved in water, if you take a tank of carbon dioxide, so here is a tank of gas, and I have this tank of gas and it's carbon dioxide, right? And if I have a little hose like this, and I hook it onto a soda bottle that just has water in it, and I open up the valve, carbon dioxide will fill up this space, just like gas fills up any space, right? And depending on the pressure that's coming out of here, I can build up the pressure pretty high. And as I build up the pressure, it's essentially increasing the number of collisions that occur between the carbon dioxide and the surface of the water. And every time there's a collision, there's a certain amount of carbon dioxide that will dissolve into the water, all right, giving us carbonated water, right? Now, it was realized that there's a relationship between the amount of a gas that dissolves in a liquid and the pressure that gas is on the surface of that liquid. All right? And this relationship, the concentration that's dissolved being equal to the pressure of the gas. Now, the pressure of the gas is in units of millimeters of mercury or torr, something like that. The concentration of the gas in the liquid is in units of molar. And so we have to have a constant that fixes those and relates molar to torr, or millimeters of mercury. So this is the pressure of the gas, and this is the resulting concentration that you'll have for every given millimeter of mercury in the solution, in molar, right? These constants, however, differ based on the kind of gas, because different gases have different degrees of intermolecular forces that can dissolve in water. So, if we are asked a question like this one here, what's the concentration of dissolved nitrogen in a solution that is saturated in N2 at 2 atmospheres? At 2 atmospheres. So essentially, instead of carbon dioxide, we're talking about N2 now, right? And it doesn't matter how much water there is. It doesn't matter the size of this container. All it matters is the resulting pressure, which is 2 atmospheres, in this case, given to us. And we have to have our constant, which shows us that there's going to be 8.42 times 10 to minus 7 molar for every millimeter of mercury. Now, do you remember the relationship between atmospheres and millimeters of mercury?
Oh, it was like 760, right?
760 what?
760 millimeters of mercury or torr for every atmosphere.
That's right. So if I want to convert this to millimeters of mercury, 1 atmosphere was 760 millimeters of mercury. So I'm going to take 2 times my 760. And that's 1520. All right. So I have 1520 millimeters of mercury. This is how much molar I'm going to get for every millimeter of mercury. So 1520 times that, which is how many millimeters of mercury I have here, should give me my concentration in molarity of my nitrogen gas, 8.42 times 10 to the minus 7. Okay, so 0.0013 molar of nitrogen gas in my solution there. Now, we're going to have a lot of problems like, well, not specifically about this kind of thing, but a lot of problems about identifying the concentration of a solute in a solution in different units and so forth. And so we really have to depend on, because there's going to be so many different kind of ways that we do this, we're going to forget. And so you don't want to memorize this method exactly. What you want to think about is these units, right? What does this unit mean?
That's big M, moles per liter.
That's right. And we're saying the resulting molarity, that's a concentration, per unit of pressure. And then we were given this unit of pressure. We're asked what the concentration is, right? So from a unit analysis, just analyzing the units, unit analysis, right? I see I have concentration and molarity over pressure, and then pressure, and I'm asked for concentration, right? How can I get concentration if they give me these things? Hopefully I can look and see that the multiplication of these, my units will drop out and I'll have my concentration. All right? So again, we're really going to have to rely on our unit analysis because I don't think it's feasible to be able to remember every single method that as we move forward here. What do you think? When you open a bottle of seltzer, it fizzes, right? Carbonated water. How should you store it to increase the time before it goes flat, meaning all of the carbon dioxide comes out of the water? Heat it and pressurize it?
Well, you said heating decreases the solubility, right?
That's right. Heating decreases the solubility of gas in all liquids.
So cooling it would be better. And increasing the pressure also increases the amount of gas that dissolves, right? So it looks like B.
That's right. If we were to heat it and then reduce the pressure, that's not going to help because, well, we already know, cool it and reducing the pressure. Cooling it is better for improving solubility, but we need to maintain the pressure, right? Now, have you ever taken a can and said, I'm going to shake this up, this can of soda, shake it up and put it in front of my buddy, and when the buddy opens the can, it squirts all over them. Have you ever done that?
Yeah, I think I did that once, or I saw it in a movie or something.
Have you ever done it and it was lackluster? In other words, it didn't really squirt all over the place.
Yeah, that happened too once.
So oftentimes somebody shakes up a can, sets it down, and then the buddy doesn't open the can maybe for 10, 15 minutes later, right? Well, just because you shake it, that carbon dioxide, which will come out of solution, and in the can then, you'll have the carbon dioxide separating from the water. Once you set it down, the pressure has increased because there is now more of the carbon dioxide trying to come out. But at that high pressure, the rate at which it'll dissolve will increase as well. And so if you just set it still and let it rest, and especially if you cool it, that carbon dioxide will redissolve back into the can. So if you really want to trick your buddy, after you shake up a can, you need to somehow ensure that they open the soda as soon as possible. Okay, good place to stop.